Yeah. So you know that each math course, algebra, statistics, probability if you're to separate it out, trigonometry, geometry is the same thing. But each, even arithmetic, there's a fundamental theorem of arithmetic. But each math course you've done over the years has a fundamental theorem that goes with it. Okay, so the fundamental theorem of arithmetic, don't start writing anything down there, I don't know this version. But the fundamental theorem of arithmetic just says that any positive whole number can be broken up into prime factors to different powers. That's the fundamental theorem of arithmetic. Fundamental theorem of algebra is just says that if you have a polynomial equation, the number of solutions that it has is equal to the degree of it. It's more or less what it says. So there's one of those. There's a fundamental theorem of calculus, which you're going to learn today. It was about the 18th century, 1700s. It was Leibniz, Newton. We're going through this process that we've been going through, where they were looking at curves and trying to figure out that connection between the velocity curve and the distance you've traveled or position. And notice that idea that we've seen with the Riemann sum, where you can go ahead and add up the sums of the areas of the triangles underneath the curve and get an approximation of what they later came to call the integral, which represented the position or distance you've traveled, the total distance you've traveled. And so they started seeing a connection between these two. And so the fundamental theorem of calculus says, and it has some given parts to it. Given parts are important. The fundamental theorem of calculus says if f is continuous at every point of a closed interval AB, so we've seen that in our other theorems, continuous on a closed interval AB, and if f, big F, is any antiderivative of little f on that same interval, then, and we call this the evaluation part. In your textbook, they break it up into part 1 and part 2. It doesn't really matter. There's 2 parts. This is the evaluation part. It's always true, and you can write this down, the integral from a to b of little f of x dx is equal to big F evaluated at the upper limit minus big F evaluated at the lower limit, where big F is the antiderivative. So the good news is you've already done all the legwork. Like, we saw secant squared the other day, and we knew that secant squared was the derivative of tangent of x, right? And we saw e to the x the other day, and we know that e to the x is the derivative of itself, right? What's the antiderivative of 1 over x? Can you think backwards on that one? Which one that was? That's one of the trickier ones. ln, good. So ln of x is the antiderivative of that. So it's like you don't even need a new list. You don't even need new cards made or anything. You already know that each of those derivatives on your card, it's now you're going the other direction. That's the integral. We'll just flip the card back over to the other side, and there it is. They're related. And so they discovered that if you can find the antiderivative of this function little f, then you can evaluate the definite integral. So that was huge. Not only that, but they also discovered that the 2 operations, and we saw this in the very beginning, are inverses of each other. So the derivative undoes the integral. The derivative undoes the integral. And then there's all kinds of things that come out of that. As a matter of fact, we're going to discover and spend some time on this next week because it's a big idea within AP Calculus curriculum. And that is, you can use the integral symbol to define a function, just like we would use a square root symbol to define a function. So they will give you functions, or just like you could use a differential to define a function too. We haven't done much of that, but they will give you functions that have an integral sign in them. Just like I've given you, or you've seen or worked with functions that have square roots in them, and x squareds on them, and some things like that, or sine or cosine. Just like that's an operation, the integral is like an operation. And so you won't always be able to find the antiderivative of big F. You need to understand that. But you can still, with the help of the calculator and so forth, and with the help of the fundamental theorem of calculus, still do things like find the max, min, points of inflection, increasing, decreasing intervals, concave up, concave down, because of the fact that all that comes from the derivative. And if you take the derivative of the integral, it cancels out the integral sign, and you got it. So if you can just, and you can do that on a calculator. You can tell the calculator, you can define a function on the calculator with an integral on it, and then say, okay, calculator, graph that function with an integral on it, and it'll do it. And then you could go and find the derivative of that function with the integral in it using the operations on the calculator, and find where that function crosses the x-axis. Those are your zeros of the derivative, which would be the critical points, right? And then tell me things about this function defined by an integral. So we'll be spending quite a bit of time in this section. It's like we're camping on this section all through next week. Okay, so I have some activities, some things that have come through just from the people who have read the exams, have come up with just different focus units and things that they've created that are pretty good to help you understand how to work with functions with integrals. So a little bit of notation here. Once again, big F is the antiderivative, if you can find it. If you look in the back of most practice books, they have a list of integrals and derivatives. So it goes beyond what we've seen, but the ones that you've seen already are the ones that are responsible for the exam. I don't have any more to add in terms of relationships on functions. But the notation works like this. The integral from 0 to 5 of x to the 3/2. This is actually using the power rule. If you raise 3/2 up 1 power, you get 5/2. You see how that works? So if you raise this up 1 degree, you would end up with x to the 5/2, and then you just divide by the 5/2, which is equivalent to multiplying by the reciprocal. So you remember with the power rule on the derivative, we would just take that power and move it out in front and multiply. So now what we're doing is, and then drop it down a degree. Think opposite of all that. Add a degree, and then divide by power. So that's how we get this 2/5 here. We're dividing by 5/2. Does that make sense? And then, and you've done a little bit of that already. And then this bar is just an evaluation bar. So this is the antiderivative. We call it big F. This is the bar, and it's the same idea as what we did in the homework or in the assignment class the other day. So you always do. Just evaluating it at the upper limit, lower limit, and going for it. So here's what it looked like here. You can even write it out for this guy. It would be 2/5, then we put in 5 to the 5/2 minus 2/5, 0 to the 5/2, where f is the antiderivative, and then figure out the value of that definite integral. So what are the prerequisites to the fundamental theorem of calculus? F has to be what kind of function? Continuous on what kind of interval? And what needs to exist to be able to evaluate it? An antiderivative, big F. Okay. So we got this written down. Notation, good. This is kind of interesting. This is, at least this is the way I like to think about it. I like to introduce the evaluation part first, and then kind of use the evaluation part to help me understand the antiderivative part, or the part that says that the derivative undoes the integral. Okay. So let's just take this right here. Here's our integral from 1 to x. And we've dealt with stuff like this. Remember that t is just a dummy variable. Because I want to plug this x in for t, and I'm going to do that in just a minute, I don't want to have the same variable. I want to plug x into itself. So the 2t is just a different variable that allows me to find the antiderivative and then evaluate it. So I'm going to show that the integral from 1 to x of 2t dt is equal to x squared minus 1 using the evaluation part. Okay, so here's how it works. What is the antiderivative of 2t? T squared. Yeah, so it's going to be t squared. And let's just write it out. T squared, when you divide by the 2, it cancels the 2. You see that? It is just t squared. Okay. So right here, this would be equal to the integral from 1 to x of 2t dt would be equal to t squared evaluated from 1 to x. And that's using our notation that I just introduced. So the antiderivative is t squared, and then we're going to plug in the x, and then plug in the 1, and out pops x squared minus 1. So the integral from 1 to x of 2t dt is equal to x squared minus 1. What would happen if I change the bottom to 2? What would change? If I change this to 2. X squared minus 4, right? If I change it to a 3, it'd be x squared minus 9. So anything that changes is the constant. We talked about that before, right? So changing this bottom part just changes, it shifts the function up or down. So remember, this is just a function, and it's equal to this. We can actually find what the function is in something that we recognize, very recognizable, right? Parabola opening upward, going through 0, -1. Can't always do that, but in this case we can. So here's the big idea, the second part of this. So, back over here. What if you took x squared minus 1, or x squared minus 4, or x squared minus 9, and you took the derivative of that? So if I asked you to take the derivative of this guy right here, so I said d dx of x squared minus 1, we would get 2x. Okay. So relating that up here, if x squared minus 1 is equal to this integral, would you agree that this is equivalent to d dx of that? If I take the derivative with respect to x of this integral, it is equal to 2x. Yeah. Because I could swap this and this. They are equivalent. We just showed that. You see how that works? So the relationship here is whatever this function is right here, whatever this function is right here, the derivative of it is the little f. Okay, they're related. That's kind of the big discovery that they came. So what is, in general, d dx of the integral from a to x of f of t dt? So even if you can't find the antiderivative, you can still evaluate the derivative of the integral. Now a must be a real number, okay? And it's going to go from some real number up to x. And it doesn't matter what real number it is because that only makes the function differ by a constant, and the derivative of a constant is 0, so it would exit out. So in general, you need to write this down, d dx of the integral from a to x of f of t dt is equal to, is it big F or is it little f? It ends up being little f because this is big F, but the derivative of big F is little f. So this is f, and what is it evaluated at? Remember, when you take the derivative, what's going to happen to the constant? It's like if I took the derivative of this guy, the derivative of 1 is just 0. So the derivative with respect to x of whatever this is will be 0. So this is going to end up equaling f of x. Let me demonstrate that to you, okay, in a two-step process like I just did here. This helps me to understand it, and then I'll give you the second part of the fundamental theorem calculus. So let's just leave the d dx off for a minute. But we got d dx of the integral from a to x of f of t. So this is more theory. The antiderivative of little f is big F, right? So we'd have big F of x minus big F of a. Are you with me so far? That's just this part right here. So, okay, now let's apply the derivative. The rules of derivatives, just like the rules of integrals, say you can apply the derivative to each part separately. So so we got this, d dx big F of x minus d dx of big F of a. That's what I have so far. I'm just taking and applying the derivative to each and every term of this binomial. Okay, what is the derivative with respect to x of big F of x, regardless of what the function is, little f of x? It doesn't matter what the function is. Now, I have to add, remember the chain rule? Chain rule comes back into it. So if x is not just x, it's something else, we got to deal with that. And it's not hard to deal with. It's just kind of reversing that chain rule. So keep that in mind. Minus, what is d dx of f of a? 0. Always, yeah, always. It will always be 0, which is f of x. So are you convinced now that this is true?
Yeah.
So d dx of the integral from a to x of f of t dt is f of x. Now, one more time, I'm going to tell you that if there is a composition of functions which you will know, because that x won't be an x, it will be an x squared, or a 3x minus 2, or it could be a tangent x, it could be anything, okay, because we have the chain rule, then you just have to deal with that, and we'll get to that. We'll show you what to do with that. It's intuitive if you understand what I just did here. If you understand what I just did here with this big idea, it's actually pretty intuitive. We've got to take this, the chain rule, and then the rules that we just talked about yesterday for rewriting integrals and stuff, and then we can evaluate it. So and there's a lot of this on the AP exam. They put this in the multiple choice part. We usually couple them on there, and then the free response will show up again too. So, any questions? Okay, let's write down. Okay, we'll just move along. Write down the second part of the fundamental theorem of calculus, the FTC. It says if f is continuous at every point of AB, you already wrote down that part. So, then the function big F of x equal to the integral from a to x of f of t dt has a derivative at every point in that interval, and df dx equals d dx of the integral, which equals f of x. In other words, when you take the derivative of the integral, the derivative cancels out the integral. Whoa. Just like square rooting cancels out squaring.
Big F is the antiderivative.
Yes, big F is the antiderivative, which you don't always know explicitly. Like you don't always know it, and this is still true.
Little f is just the function.
Yeah, it's the function. Yeah.
The integrand?
It's the integrand, yeah. And so, you know, with the other day we had a little f that was secant squared. Big F was tangent. Yeah. So big F is going the other direction from what we did last semester. It's what we call the integral or antiderivative. But there's a relationship between the two functions. So that's it. There's two parts to it. And that's the two parts just say if there is an antiderivative, then you can actually evaluate it by plugging in the upper and lower limits and subtracting the numbers. You can do that. And then regardless of if there's an antiderivative or not, the derivative of the integral is the integrand. So I have to write all that down. So on this next example, write down this example. I'm going to see if we caught what I just said on the previous slide. Let's see. There's an easy way to do this, and there's a hard way to do this.
There's also ways.
What's that? The antiderivative right here. The antiderivative is, well, it has this as its derivative. So that's the definition of the integral.
So should that be df dx equals the integral?
Nope. Nope. The antiderivative is the integral. I'm telling you that, I guess now. The antiderivative is the integral. What's that? But if you take the derivative of the antiderivative, then you get the integral. So, or the integrand, sorry, you get the integrand. You get what you're taking the integral out. You're thinking too hard about it. I'll give you some more examples. So, right, this example is, let me just show you this example, and you have some in the assignment you're going to do like this. So guys, here we go. In this one, it's asking for, well, first of all, let's back up. Could you get the integral of this guy? Could you evaluate it? Yes. What allows you to be able to evaluate this one in particular? The fact that you know the antiderivative. But you don't have to know the antiderivative to get the answer. The derivative of the integral of cosine of t dt, you have to be able to tell me what it's equal to without going through the process that we did 2 days ago. Yes, it's equal to cosine of x, and you're done. This is equal to cosine of x. That's what the second part, or the antiderivative part of the fundamental theorem of calculus says. You can go through the process. Oh, maybe we should do it again because there's confusion. You can go through the process that we did the other day. Okay, you could tell me. So, what is the antiderivative of cosine? This sine. And the derivative of sine is cosine. So we don't need to worry about sine. Negative, positive. Okay. So we have d dx. If the antiderivative is sine, what does the evaluation part say the integral would be equal to? Sine of x minus sine of negative 5. Good. Okay.
And that alone is integral, right?
Then d dx of sine of x minus d dx of sine of negative pi. If you really want to, you guys have the toolkit to figure out sine of negative pi, but all you really need to know is sine of negative pi is a constant, and the derivative of a constant is 0, so this is 0. And then you guys were with me last semester. I recognize all of you. The derivative of sine is cosine. That's okay. So we're going to revisit all of this. So this is cosine x. So
do all the work. Throw the derivative back on.
Yeah.
It's simple.
The derivative of the integral is the integrand. Yes.
And why would you want to know?
What's that?
Because you can just look at the integral.
Right.
There.
Right.
So why would you want that?
I'll show you. I'll show you. We won't be just dealing with that. You guys, listen. We aren't just dealing with definite integrals along the way. We're going to deal with what are called indefinite integrals. So we're going to do all the same things we did last semester. So last semester, that last chapter, the applications were we took a function, right? We took a function. Here's the application of the derivative. And a lot of them were word problems. So we took a function. We had to take the derivative of the function. And then we used the derivative of the function to find maxes, mins, and then intervals over which they are increasing, decreasing, point of inflection where it was concave up, concave down, but primarily it was maxes and mins. That's what those different problems are about. And so here's what will happen with this, is you can graph the derivative of a function defined by an integral and then do all that same stuff again without ever being able to know what the antiderivative is yet. We haven't seen anything like that yet. So guessing this, it's trivial, but that's not the case always. And there are full courses, like ordinary differential equations is a course made up of functions that are derivatives. They have derivatives in them. Like the derivatives are what helps to make up the function. They're defined with derivatives. And then like you can have multiple order derivatives and things like that. But it's the same thing with integrals. Integrals can define functions. You can have a function with an integral sign in it and not necessarily know what the antiderivative is, but still do all the stuff we did last semester. So, I'm getting there. It's going to take a little while to get there, so bear with me here. But oh, what was this? I forget what this was now. Okay. Okay, we did that already. And then I've already asked this question: what if I change the lower limit to pi over 2? Will there be any difference in the results? No. Won't matter, because pi over 2 is a real number. When I evaluate that real number, I get a constant. Derivative of the constant is 0. So, just moving right along. Functions defined as an integral. Okay, so this is our first function. Here you go, Jeremiah. Our first function. You don't know the antiderivative of this, but you can still evaluate the derivative of the same. So this is a, if I take this off, dx off, that is a function defined as an integral. I've defined a function. It's going from 2 to x, and it's the integral of square root of 2 plus cosine of t dt. You don't know the antiderivative of that. So you have to use this second part of the fundamental thing of calculus to find the derivative. So we can find the derivative of it. We can't find the antiderivative directly. But if we can find the derivative of it, then we can find the max and min where it's increasing, decreasing. Like we could go and sketch this whole curve, whatever the heck it looks like. The calculator, of course, does it too. And we do a lot of that. But it's like, I think the calculator does so much, but that's the idea too. Like you got to think, before they had this technology, they could take a function, find its derivative, which is easy, and then produce a sketch of what it looked like. Characteristics. So that's how they analyze function. So what is d dx of the integral from 2 to x of square root of 2 plus cosine of t dt? What does that equal? It equals square root of 2 plus cosine of, the only thing it changes here is x. Yeah, it's because, yeah. And that's it. That's it. This is the derivative of the integral of this function. Because the derivative and the integral cancel each other. Yes. Evaluated at the upper limit. And that we got to add that evaluated at the upper limit, because if the upper limit is not just x, we've got to apply the chain rule.
So what do you do with the integral?
What's that?
What do you do with the integral?
I'm getting there. Okay, so the next step here, the next step in the process is this. So, okay, what if the upper limit is not just x? What if it goes from a real number up to something like x squared? In other words, we have a composition of functions. We already have a composition of functions right here. But here's another layer, I guess, of it. So what is d dx of the integral from 3 to x squared to the square root of 5 plus t cubed dt? Okay. Well, based on the fundamental theorem of calculus, I do know this. I know that it's got to be equal to. Go ahead and write that down. All right, so according to the fundamental theorem of calculus, this is equal to the integral of, or is equal to the square root of 5 plus something cubed. What goes into something cubed? X squared, yeah. But according to the chain rule, what does the chain rule say we have to do with the inner function? Take the derivative of it, right? So times d dx, what is the inner function here? X squared. Yeah. That's all you have to add to it. because of the chain rule. And so this is equal to, in simplified form, 5 plus x to the 6th times d dx of x squared is 2x. So they have, these are the types of problems they have relating to the fundamental theorem of calculus on the multiple choice portion of the AP exam. So they probably won't have something as simple as this. It might be as simple as this. It probably will actually look like what I'm going to show you next, which combines not just the fundamental theorem of calculus and the chain rule, but those properties of integration, rules of integration that we just saw the other day. I'll show you what I mean by that. So we have this one right here. If it matches the formula that I gave you for the fundamental theorem of calculus, it goes from a to x. You just pop in the x there. That's really all you have to understand at this point. We'll get a deeper understanding of this stuff as we go into next week. We're going to, like I said, I have some stuff just to work on this next week, and I have some practice AP pre-responses that relate to this. You'll feel better about this by Thursday next week. And then the next layer up is when this upper limit is a function other than x. You do have to take d dx of it. I mean, you could say we're taking d dx of this, but the derivative of x is just 1. So you're always using the chain rule.
We're taking the derivative of the integral and then derivative of the integration.
No, derivative of the inner function.
Of the integral.
Yeah. So it's just the chain rule. We're just doing the chain rule. Alright. So then we get to the next level here. This is the next level, believe it or not. So what have I changed here? The lower limit is no longer a real number. Okay. So there should be some chain rule stuff in here, but here's the deal. I've got to make this thing, this integral, match that format where it goes from a, little a, up to a variable expression. Okay. And here's how we do it. I'll let you go ahead and write this down first. d dx, so the integral from x squared plus x to sine of x. Cubed root, that's a cubed root of t plus 2 to the 4th dt. And
Can't wait.
All right, so here we go. Here we go. So what needs to happen here is I need to go from a real number up to sine of x. And then somewhere in here I need to flip things around. Remember the order of integration rule? That was the first one, where if you switch the limits of integration, top and bottom, it just changes the sign. So I'm allowed to switch the limits of integration when we're going to do that. And then there's another one called the additivity. You remember the additivity one? I can go from the integral from a to b, and then from b to c, and that's equivalent to going from a to c. So we're going to put those two ideas together to rewrite this integral so that it looks like the original formula that I gave you that says integral from a up to x. So I need to make this match that before I can apply the fundamental theorem of calculus. That's the big idea. So what if I rewrite this, just this part, we'll put the d dx out here first. So the d dx is just going to hang around out here for now. d dx, and then I'm going to rewrite this guy. It's two separate integrals, but let's just do this. We can go the integral from x squared plus x to, and because when you take the derivative of it, when you have a real number up here and you take the derivative, it's just going to be a derivative constant will be 0. So I can choose any value I want to be my upper limit. It won't matter. So I'm going to just choose 0. Choose 0 here. And then I'm going to put in the function cube root of t plus t to the 4th dt. And this is, if I were writing a proof for this, this would be called because of additivity. So I'm going to go with integral from 0 up to sine of x of the same function. So that's cubed root cheating, yeah. Cubed root of t plus t to the fourth dt. Okay, and if you're, as you're taking notes, you might want to just note that this is due to additivity. This is additivity rule. And the additivity rule simply says that the integral from a to b plus the integral from b to c is equal to the integral from a to c. Okay, so are you guys with me? So I write down the additivity rule. So it might be helpful to see it. So the integral from a to c is equal to the integral, I'm not even going to put the function in here, but integral from a to b plus the integral from b to c. That's what it says. And that's what I just broke this up into, and that's what you'll need to do on these. Okay. So that's the first step. Okay, now, this one matches the previous example. This piece of this one, we could apply the previous example to it. What we would do is we would put sine x in place of t, and then do the derivative of sine x and multiply it by that. So that one's done. This one does not quite match this one. Can I make this one match this one?
Yeah.
Yes. And this is most likely what you'll see on the AP exam. It'll probably be this level. On the practice ones, it typically is. So I'm back to red. Okay, so d dx. So d dx, what am I going to do with this guy right here? Flip it, yeah. So we're going to put it'll go integral from 0 to x squared plus x, and we're going to put a negative sign out here. Big negative sign right there. Of the cubed root of t plus t to the fourth dt plus the integral from 0 to sine x cubed root of t plus t to the fourth dt. So we're just going to flip, and that's the order of integration rule. And you'll have to do that each time. You're going to get a chance to practice that before you leave today. So order of integration rule, which just says that the integral from a to b of f of x dx is equal to negative the integral from b to a f of x dx. Hi. We are about ready to apply the fundamental theorem of calculus to this. Okay, so by the fundamental theorem of calculus, what is d dx of this first part? You got a negative sign in there, right? Negative sign. And then we've got to plug in the upper limit for the variable, the dummy variable t. Okay. So we're going to have x squared plus x in place of these. We'll just put them in. I'm not going to even try to simplify this. That's asking for trouble. That's fine. So we've got x squared plus x, that goes in for the t, plus x squared plus x to the fourth times d dx. I'm going to write it. I'm going to show my work here. d dx of x squared plus x. Okay, and then if you want to skip this step, if you're following, that's fine. But and then plus, and then I got the same thing again, but I'm going to put in sine of x. So it'll be cubed root of sine of x plus sine of x to the fourth and then times d dx of sine of x. So So applying the derivative of each one of these, I've used the fundamental theorem of calculus. So final answer, negative cubed root x squared plus x squared plus x to the fourth times 2x plus 1. That's the first part of it. It's taking the derivative of x squared plus x plus cubed root of sine of x plus sine of x to the fourth times derivative of sine of x is cosine of x. And I'm done. That's as hard as it gets. So you'll have like one or two of each type of these three examples whenever. So one where you have just an x on the top, one where you have something other than an x on the top, and then one where you have a variable expression top and bottom. I think there's a couple of those in the second. And you know, as you're practicing them, you will have one like this on the exam. Hopefully not. It won't be as messy as this. But they do like to do things like they do like to plug like a trig function into it. I'm sorry. They're trying to test you on, you know, all your different derivatives, right? So they could put a couple different types of functions, top and bottom, and they are testing to see if you know your derivatives for those functions as well. So they're very rich problems. You'll see it's rich. In other words, they require a depth of understanding. Very high. Right. So now we've seen, you already saw, and we're going to practice it a little bit more, but yet in last night's assignment, you kind of already got to play with the evaluation part, we call it, the evaluation part, where if you know the antiderivative, you just plug in the upper and lower limit, subtract and get the answer. This is now the other part of it.
So is this finding the function that is the derivative of?
Yes.
Okay, so this is just trying to work backwards to find the different function.
Okay. All right. So summary, and we'll do some practice.
Was it practice?
It was. Well, I was doing it, but you're going to try on your own, so you can do it. So what is the first part of the fundamental theorem of calculus? The inside closed interval, and if the integral is the integral is equal to the antiderivative, and what do you do with the antiderivative? Yes, you plug in the upper limit and the lower limit, and you subtract them, and there you go. You got it. I don't know which is part one. In the textbook, yes, that's actually part 2. It's in the textbook, but it doesn't matter. I just plug the evaluation part and the antiderivative part. The evaluation part is what Sean just described. If you know the antiderivative, you plug in the b and the a and subtract them and get them. Okay, that's the evaluation part. And then the second part is same prerequisites, right? Continuous function on a closed interval. Has a derivative at every point of it, and the derivative can be found by you take the derivative of the integral and you get the integrand evaluated at the upper limit. So in words, it's saying that the derivative and the integral really are inverses of each other. And when we specifically write it out or define a function with an integral in it, like we would define a function with a square root symbol in it, that if you take the derivative of that, it's just the integrand evaluated at the upper limit. Those are the two parts. Calculus is easy.